After working some problems related to gradient divergence, curl and the second order derivatives, let's now move on to the vector integral calculus. There are three different types of vector integrals: line integral, surface integral, and volume integral. Let's start with the first one, that is line integral. As the name suggests, this integral is performed over a line. So, if we have a line starting from point A to point B, this may be any line, a straight line, a curve or something else. We have a vector v, we have a dot product of this vector with a line element dl, and that represents a line integral. We can often have another type of line integral, that's over a closed line. Closed line means this line encloses a surface v dot dl over a closed line. This type of integral is also quite useful in the context of electromagnetism, that we will see later on. Now, let's have an example to understand how line integrals are calculated and what it means. So, the example says calculate the line integral of the vector function v, that is expressed as y square x cap plus 2 x y plus 1 y cap. You can clearly see that this vector v is a two-dimensional vector, and start from point A, that is given by 1 1 0, and end at point B, that is given by the coordinates 2 2 0. So, what can be the paths for these 2 points for this line integral? There can be many paths connecting these 2 points. So, the first point is 1 1 0, let us say that point is here. The second point is 2 2 0, let us say that point is here. So, this is point A, this is point B, and we will consider 2 different paths here. One path will take us this way, the black line. The other path will take us along the blue line. So, let us consider the black line first. the expression for dl, the line element, is given as dx x cap plus dy y cap plus dz z cap. This is always true, and for the given vector v dot dl can be given as y squared dx plus 2x y plus 1 dy. Now, in the black path, we will have in the first segment we will have y equals 1 always. This is x axis, this is y axis, and that means dy equals 0. So, over the first path, we have v dot dl equals y square dx, y is 1. So, this is 1 dx plus, because dy is 0, the second term becomes 0. So, the integral over x equals 1 to 2, 1 dx is given as x from 1 to 2, that is 2 minus 1 equals 1. Now, we will have to go for the second segment. In the second segment, we have x equals 2, which implies dx equals 0 for x being constant. So, v dot dl, this quantity will be 2 times y plus 1 dy, that is 4y dy plus 4 dy, and the integral will be over y only, because only dy terms survive here. So, integration over y equals 1 to 2 v dot dl equals integration y equals 1 to 2 4y dy plus 4 dy equals 4y squared over 2, the limit being 1 to 2, plus 4y, the limit is 1 to 2. This is equal to 2 times 2 squared minus 2 times 1 squared plus 4 times 2 minus 1, and this is 8 minus 2 plus 4 equals 10. So, the sum of segment 1 and segment 2 becomes 1 plus 10 equals 11. Now, let us move on to the blue path in the example. On the blue path, the equation of that path is x equals y. So, dx equals dy. If we have that, then integration from point A to point B v dot dl, this can be expressed as integration from 1 to 2, we will substitute y by x, we will have 3x square plus twice x dx, and we are supposed to perform the integral. This will become x cubed, the limit being 1 to 2, plus x square, the limit is 1 to 2, that is 8 minus 1 plus 4 minus 1 equals 10. So, we can see that the integral along the black path is 11 and along the blue path is 10. So, it is not necessary that the line integral along every path will be same if you connect 2 points in the line integral for a vector. It can be path dependent. There are certain cases where the vector integration, line integration of a vector is not path dependent. We will come to that situation later.